Okay, my friends, we're back with another dynamics problem on work and energy. This is a hard one, so let's see if we can solve this one, okay? We're going to use our work and energy equation. What we have here is just kind of set this problem up in a really nice way so it's going to be easy for us to solve, okay? And if you'll do this, kind of an energy balance on these problems, I think you'll find that this will make it a lot easier to kind of set your equations up because we kind of have a before and we have an after, right? And so we have to add these things together. This side needs to add and equal to that side, okay? So what we've got is two blocks here on an inclined plane. So the velocity, find the velocity of the blocks, okay, once they're released. So initially we're holding them in place and then we let them go and whoop, they start sliding. Okay, so one block is heavier than the other. This one here is 60 pounds. However, this one over here is only 40 pounds. So this one being heavier is going to slide down while this one slides up. So we're going to kind of get that action there. And they tell us that block B moves 2 feet up the incline. Okay, so it goes from here to some point over here, and it's going to move 2 feet. Okay. Now, one of the things that you need to do, you need to go way back to our videos when we started talking about relative motion and kind of remember if one block moves and we've got pulley system here, how far does the other block move? Well, there's a relationship between block B and block A because they're tied together, aren't they? Okay, so we need to remember that relationship, and that relationship here is pretty easy. Here's the way I think of this. You know, if this guy moves 2 feet, then this guy over here, since he has 2 ropes, 2 feet worth of rope, they're going to get a foot out of this one and a foot out of this one. So this guy is going to move half as fast as that guy over there. So for the velocity of A to equal the velocity of B, which is moving much faster, I'm going to have to do 2 of those, aren't I? So 2 velocity A's equals 1 velocity B. And this is kind of what I would call a compatibility equation, okay? So there's one kind of equation that we're going to need. And the other equation is distance, and it's the exact same thing. If this one moves up the ramp 2 feet, how far down the ramp? Oh, you know what? Let's put a negative in front of that. Since one's moving up and the other one's moving down, they're moving in opposite directions. We'll put a negative in front of that. But the distance, if this guy moves 2 feet, what does that guy do? Well, again, 2 feet of rope. I got a foot there and a foot there to take up that 2 feet of rope. So if he moves 2 feet up, this guy moves 1 foot down, okay? So I know that the distance of this guy is going to be 1 foot, okay? That's a 1 foot. That wasn't very good, was it? There you go. Okay, so there's some compatibility equations that we can come up before you ever even start the problem. Now let's see if we can fill in our energy balance here, okay? So number 1, the kinetic energy of block A and block B. What is kinetic energy? Kinetic energy is, here's the equation for this chapter. T1 plus the sum of all the works from 1 to 2, from phase 1 to phase 2, or what we would call that. And then equals T2, the kinetic energy. So this is kinetic energy. This is work, which is potential energy plus, well, all the potential energies. And then this guy over here, again, kinetic energy. And kinetic energy is equal to 1/2 mv squared. Now we know what this guy is. We did this in the very last video. So if you don't know how to find work from one point to another, then go back to the last video and watch that right quick and then come back over here and rejoin us, okay? So what does kinetic mean? Kinetic means moving, in motion, doesn't it? Okay? So what do you think the kinetic energy at the first point here is? Now, they said that initially the blocks are being held in place, and then they're released and they start moving. So when they're held in place, what's the kinetic energy? Well, we know that it's 0, isn't it? Okay? Now, what is the potential energy, which is kind of rho GH, right? It's the mass, mg, times the height that it's going to move. And in order to calculate that, I think maybe it's easier to see if we drew a free body diagram right quick. So let's draw a couple. I'll draw one for block A. Okay, here's block A. And let's see what's going on in block A. They tell us that this is 60 degrees. Okay. And what do I have here? Block A has this. Whoop. It has a weight of 60 pounds. Okay. It has a normal from the hill there, normal for A. Now, it has friction. There is friction on this hill. They tell us that the kinetic coefficient of friction is 0.1. So as these are sliding, these are not slick hills. They're not made out of Teflon, because nothing sticks to Teflon except pans. I'll explain that to you later. And then the friction, since block A is sliding down the hill, friction is going to go up the hill, right? So here's friction A. Okay, anything else acting on that? I don't think so. Oh, I do think so. Look what else is acting on that. The rope over here. I've got 2 ropes acting on that. Okay. Okay, so, and then block B, here's block B over here going this way. Whoops, let's make enough room for him. Here's block B. Okay, and block B weighs 40 pounds. And again, they give me the angle here of 30 degrees. Okay, and then I have a normal force, the normal from block B, and I have a tension from the rope. Okay, and I also have friction, don't I? Just like I had friction up here, the friction, since this block is sliding up the hill, friction is going to go down the hill. There's friction from block B. Now the rope is not really doing any work. He's not the thing doing the work. Who's doing the work here? Gravity's doing the work. The rope is not an external force that's pulling on anything. It's just tying the 2 blocks together. So the rope isn't going to do any work. Only gravity is going to do the work. So only that force there. And then we have to think about the friction from the the friction force. Okay. And so let's see here. If you're 30, then you're 60. If you're 60, then you're 30 degrees, aren't you? Right there, 30 degrees. And if you're 60, then, oh my goodness, let's see these angles here. If you're 60 degrees, then you're 30 degrees. And if you're 30 degrees, then you are 60 degrees right there, right? I see so many students messing up on just simple things like, what is the angle? And just work your way around. If that's 60, then that's 30. If that's 30, then that's 60. And just label it. It should be nice and easy to come up with these things, okay? So there's 2 free body diagrams of what's going on. The things that I'm going to be worried about on this problem is the weight and this friction force. The weight and that friction force. Again, the normal force doesn't do any work because why? It's perpendicular to the surface, and guess how much motion there is perpendicular to the surface? 0, okay? So let's fill this guy in, okay? So the potential energy of block A, let's see, block A is which one? Oh, that's the heavy one, right? This is block A. This is block B down here, okay? So block A, kind of rho GH here, right? So the weight is 60 pounds, okay? So remember, since the weight is going down, we're talking about that vertical distance down, okay? So if I make myself a triangle, right, we know that the thing moved 1 foot down the hill, 1 foot. So I'm really interested in this distance right here, which is 1 times the sine of 60, isn't it? Okay? So times 1 times the sine of 60. Okay, so there's that guy. Let's do the same thing for block B, right? The weight is going down. And let's see, what do I need? If that's 30, then this is 60 degrees over here. Oh, let's see. We're moving this way now, aren't we? Here's the hill, and we're moving 2 feet up the hill, and I need this distance over here, don't I? So I need 2 times the sine of 30 this time, right? So this guy is 40 pounds times 2 times the sine of 30 degrees, okay? So just think about that as if I need this guy right here, right? I need this side over here for him, right? That's 2 there's the 30, right? Sine of 30. And for this guy over here, I'll make a triangle, right? I need 2, that's the hypotenuse, times the sine of 60 gives me this side over here. So you see where those two numbers came from, right? So there's my potential energy that the weight is going to do, the work that the weight is going to do. Okay, now let's talk about down here, the work that the friction is going to do. Now what do you know about the friction? Remember what we talked about last video when we were talking about work, if the force is one direction and the motion is in another direction, then what? The work is negative, right? So in this particular case, the friction, the work due to the friction on A, the work due to the friction on B is going to be negative, okay? So we've got a negative here, both of those. And what's that going to be, okay? So we'll need to figure this out, okay? And what is friction? Do you remember? Friction is fun. Oh my. Remember, friction is mu times N. Well, we know what mu is. It's given, 0.1. What's the normal force for this guy? Okay, here's the NA, right? So I need this component right here of that 60, right? So the N here for this guy is going to be 60 times I need that guy that's adjacent, cosine of 60 degrees. And same thing down here, I've got F, this is FA, okay? FB is going to be equal to, what do we got here? I need this component right there of that 40, right? And that guy is going to be 0.1 times 40 times the cosine of 30, right? Okay, so there's my two works here, and they're going to be negative, right? So 0.1 times 60 times the cosine of 60, and 0.1 times 40 times the cosine of 30, okay? So there's that. Now let's do, after the release, what's going on. So kinetic energy, 1/2 mv squared, okay? So for block A, that's just going to be 1/2. Okay, what's m for block A? Now remember, this guy over here was a weight. It's a force, right? It's a force times distance. But this guy over here is a mass. And in the USCS system, that's going to be the weight divided by the acceleration due to gravity. So that's going to be 60 divided by 32.2, okay, times velocity of block A squared, okay? And then block B, same thing, 1/2, 40 divided by 32.2, velocity of block B squared. And then the potential energy after they release it, right? One block went up, one block went down, so potential energy is conserved afterwards. These guys are going to be 0, okay? So let's see if we can take this information that we have, fit it into this equation. You'll find this equation in your book, okay? This is the work and energy equation, right? Kinetic energy plus work equals the kinetic energy afterwards. So here's what we've got. Now, we're going to have two equations. So here comes equation number 1. Man, you almost made me mess up. Look at this. This is work. Work. What is work? It's force times distance, right? And the force is the friction, right? Which was mu times N, mu times N. But guess what I didn't put on there? You didn't put the distance on there. So B moved 2 feet, A moved 1 foot. Oh my gosh. We almost messed up, but we got it caught. Okay, here we go. I know that y'all are like, wait, I need to leave a comment, you messed up. No, okay, we got it. Okay, so here we go. We're going to build that equation. We're going to start off with this guy. What's T? 1. Well, it's 0, isn't it? 0 for block A, 0 for block B. Plus potential energies. Now, here goes the work part, okay? So 60 times 1 times the sine of 60. And remember, one block goes uphill, one block goes downhill. That's why this one has a different sign than this guy does. Okay? Minus 40 times 2 times the sine of 30. Okay? And then, oh, then we got this work. So this is the work due to rho GH, right? Now we got the work due to the friction here. Okay, and that's minus 0.1 times 60 times the cosine of 60 times 1, right? Minus this guy, 0.1 times 40 times the cosine of 30 times 2. And this gets all of our u, okay? So that business is this guy. And now we're going to go to the other side, and we have these two guys here. So we have 1/2 times 60 over 32.2 VA squared plus 1/2 40 over 32.2 VB squared. Okay? Oh, look what we have. All of this over here is just a number, isn't it? Just add that up and get a number. This over here, I'm going to have VA and VB. Oh, but look, I have a second equation right there with a VA and VB. Let's do a little substituting. Let's see if we can solve this. Okay, so 60 times 0.866, 60 times 0.866, 51.96, minus 1/2 at times 2 is 1, that's a 40. And what do we have here? 1/2 of 60 is 30, times 0.1 is 3, minus 3. And then over here I have 4 times cosine 30 times 0.866 equals, times 2 equals 6.928 equals 60 divided by 32.2 equals, divided by 2 is 0.932. And that's VA squared, the velocity of A squared, plus, okay, 40 divided by 32.2 divided by 2 is 0.621 VB squared. Okay, so there's a good equation. What does this side equal to? 51.96 minus 40 minus 3 minus 6.928 is 2.032. Okay, is equal to 0.932 VA squared plus 0.621. Oh, let's substitute VB for that, right? So -2 VA quantity squared. So that's just going to turn into a 4 VA squared, isn't it? So 4 times 0.621 and then plus 0.932 is 3.416. VA squared equals 2.032. 2.032 divided by 3.416 was 0.595. 0.595. And this is feet per second equals VA. No, I'm sorry. Equals VA squared. That's feet squared per second squared, which equals square root of that. Square root of answer 0.771 feet per second equals VA. So there is VA. So what do you think VB would be? The velocity of block B. Okay? Well, remember, velocity of block B is going to be twice as fast as block A. So all we have to do is take that times 2 is 1.54 feet per second. And if we call that one positive, we need to call that one negative, right? Because one's moving uphill, one's moving downhill, right? So we need to make sure that We differentiate that, okay? And there you go. That's so easy. That's not easy. That's a hard problem, okay? But see if this energy balance kind of method doesn't make that a little bit easier for you to work, okay? All right, I hope that made sense. We'll see you on the next video. Bye, gang.